we will move on to the next part. This is something that I thought I would cover, and what and again, not from exam viewpoint or assignment viewpoint or anything like that, just from an interest viewpoint. Okay. So, before that we will just cover the salient features of MPC. This is probably just going to be a recap of things that we have talked about. Okay. Yeah. So, MPC basic setup, you have a process, you have your measurement devices, you have a model. The model and measurements are used to compute the state information by an observer. The state information is used by MPC in order to predict the future. An optimizer chooses the best set of input moves, the current input move is implemented, and you repeat that at each time step in a receding horizon manner. Okay. Definition of MPC. So, the more important words or keywords MPC is it uses an explicit process model, it is an optimization based algorithm, and it uses model for predicting the future and is able to handle the constraints. The definition of MPC is, sorry about this a little bit, MPC refers to a class of algorithms that utilize an explicit process model to compute a manipulated variable profile that will optimize a performance objective predicted over a future time horizon subject to constraints. Okay. So, let us look at an exemplary MPC application. So, you have your plant which has input, output and disturbances. You use the input and output information with an observer in order to determine the state. Okay. The state is what I had referred to in response to his question, I had referred to that as an xk, that is what we will call as state of the system. Okay. And we will use a model of this nature in order to compute how the future is going to behave. These are going to be constraints and there is going to be some kind of an objective function. Okay. In the previous set of slides, we saw the objective function to be a quadratic objective function. You are minimizing deviation from set point, but it need not be a quadratic optimization function. It could also be maximizing the productivity of the system. So, it could be a linear objective, it could be a non-linear objective, it could be a bilinear objective. The most common is the set point objective, which is a quadratic objective. Okay. So, again let us look at the keywords: optimize, predicted future, process model and constraints, which is what you can see in these boxes over here. Okay. So, something that I talked about in words using an example 10 to 15, 11 to 16 and all that, we will just talk about the same thing using this graphic, what that receding horizon means. Okay. So, as he had asked earlier, we have reached a current point k. Okay. This is how the past input trajectory is, this is how the past output trajectory is. This is where you want to go to the set point, okay, and you want to go to the set point in the most optimal way. Okay. So, the model is used to try out a few input trajectories. Okay. Now, these input, based on these input trajectory, the model is going to be used in order to predict what the future is going to look like. Okay. Based on the model's predictions of the future, an optimizer determines what is the best or the most optimal trajectory. Okay. What you see over here is that it is predicting the future for a certain time horizon, and this horizon is called prediction horizon. Okay. We want a prediction horizon typically to be as long as possible. Okay. But we are trying to change the input moves for a shorter time duration in the future. Okay. And that is called control horizon. Okay. We will represent prediction horizon as P, we will represent control horizon as M. Okay. If we have infinite amount of computational resource, we would typically want M and P to be infinity. Okay. But we only have finite computational resources, so we have to be judicious about the choice of P. We want P to be as long as possible, but we want M to be reasonably long, that does a balance between performance and the computational requirements. Okay, both of them have to be met. Okay, and again that is the reason why. So, if you look at the theory of optimal control in 1960s and all that, M and P were all infinity, but in MPC M and P have been finite. Part of the reason is because it originated in industry to solve a specific set of industrial problems. Okay, so all those constraints were also naturally incorporated in the MPC algorithm itself. Okay. So, now you determine what is the best control action, you are only going to implement the current control action. Okay. Now, when you implement the current control action, we know that the model is not perfect, it is not perfect representation of the system. So, instead of this system going on to the predicted point, it has gone on to another point which is close to that predicted point, but not exactly the same as the predicted point. So, we cannot implement the entire M set of control moves right now. So, we will only implement one control move, okay, and at the next time instant repeat this entire process. So, 10 to 15, 11 to 16, 12 to 17, 13 to 18, this 5 time steps into the future is going to be repeated every time we move in the system, and this is what is known as a receding horizon. Okay, that is a good question. The question is, computing 4 extra moves in the example that I gave, isn't that a waste of computational resource? So, this is something that we will come to in week 4 of this course, is what is an appropriate choice of M. You want M to be larger because larger time in the future you predict, better is your performance going to be. Okay. For example, let us say the system has inverse response. Okay. So, you want to be able to manipulate a longer time into the future. Okay. Not just predict long time into the future. If you only allow prediction for long time in the future, but manipulation only for one time step in the future, okay, it is going to move in the direction that will take your future where your set point is. Okay. So, but if you allow 5 time steps into the future to change your input moves, it will go in the opposite direction, okay, and then as the system starts responding, it will immediately come back, and you will see examples of that happening in week 4. Did you have a question? No. Okay. Okay. So, maybe I can also try to answer this question in an analogy to chess. Okay. So, let us say you are MPC and you have your opponent which is the plant. Okay. So, your opponent makes a move, okay, you are going to make a move. Okay. How do you make a move? Based on opponent's current move, you kind of try to predict what opponent's future moves are going to be, but you are not going to predict only one future move, but you are going to predict 5 or 10 or 15 or 20 future moves. Okay. But when you are predicting your opponent's future moves, you are not saying that I am going to sit do nothing. You will say that maybe I will move this, then my opponent will move this, then I will do this, then my opponent will do this, then I will do this, then my opponent will do this, and that way you are trying to determine the best chance of you winning the chess game. Okay. So, is this the best move? Is this the best move? Is this the best move? Oh well, I do not want to move here because then I will lose my piece. Okay. So, based on that you are taking a call on what are the moves you are going to implement. Okay. So, at each time it is an expanding problem. There will be a small set of future move. For each of the future moves there is another small set. For each of those future moves there is another small set. So, if you look at the number of sets long time into the future, the options, the combinatorial options are very large. So, we need some kind of an optimization in order to determine what is the best input moves, but you are not determining just one input move, you are determining multiple input moves. Okay. Just an answer again to one of the questions, if you are looking at only one input move to the future, you will never be sacrificing any of your pieces. So, you have seen this happen in chess, right? I will sacrifice my bishop in order to win this game. Why are you sacrificing the bishop? If only one input move was the only thing that you are optimizing on, you will never sacrifice a bishop, because that input move where you are sacrificing the bishop is 100% the worst input move that you can make. But because you are saying that I will determine 5 or 6 time steps or 10 or 15 time steps into the future, you are willing to sacrifice your bishop. Okay. Again, and what is something that differentiates me from let us say Vishwanathan Anand? I can look at 2 or 3 time steps into the future. Vishwanathan Anand probably looks at 25 time steps into the future. Another difference might be that he has a much better model of what the opponent is going to do than I have. So, it is not just about the model, it is also about how far into the future can you predict. Okay. So, let us get back to the components of MPC, and what that means is that you need a dynamic process model, and along with the dynamic process model you have the model state, you have the model in terms of a multi-step prediction equation, objectives and constraints, we saw about that earlier today. There is an optimization solver, and there is a way to update the state. This is something that we have so far called observer, which basically means you had predicted your system is going to reach at 12.5, but the system has only reached 12.4. So, there is a difference between of 0.1 in what you predicted and what actually happened. How can you use this information in order to update your model or update your state? That is what the questions are.